Alright, a video where I'll be as concise as I can be, and try to be, on the subject of photon polarization. So first we need to have some background on what polarization is, what a photon is. I'm arguing that a photon is a pattern, okay, that has a frequency, and the key ingredient isn't some sort of idea of a wave, that the key ingredient is that there are nodes, and that's the pattern, that's the frequency. So like bullets flying through space, light is a frequency, a number of nodes, 3, 4, whatever the minimum would be. And the trick to polarization is that light, like all electromagnetic radiation, as it's called, is created with antennas. That is, the energy has to travel through matter, atoms, and it produces the photon as it moves through the substance, and that's how it's created. And then on the small atomic scale is where high frequency light is created. So you can sort of understand that big frequencies, big radio frequencies, there's plenty of time between the nodes, the frequency. This could be a mile, lots of time, for light to travel a mile. Lots of time for the energy to get up the antenna to, create effects before the next frequency. And obviously, the antenna can't do much with extra antenna. So long antennas work for long frequencies, long wavelengths. Short antennas work for short frequencies. And light's no different. Visible light is a frequency. The polarization is proportional. All the physics sort of says, to the frequency. So the differential, the time it takes for the energy to go through the atoms at the speed of light, is proportional to the time it takes for the light itself, the bits of force, to leave. And so if you were to draw a picture of photons, they would be something like a mental picture. You could sort of understand them as bullets flying parallel, a little bit out of alignment, and with a set frequency defining whether they're red, blue, or green, or whatever color, and the frequency is proportional to this distance here. So it's like an envelope you could think of flying through space with a few dots written on it, and that would be a profile of a photon. So it's important to think about how something's produced if you're going to start thinking about how it's going to be received. So the argument is that electricity, generally speaking, is one easy way to create photons, is to run electricity through something at a high enough amperage, that is, you involve as many atoms as possible, shoot the electricity in, affect the atoms, and they'll produce the effect, which is, I would argue, just electrons moving quickly. So when an electron moves quickly, it captures all the energy between the two distances and essentially pushes it all into a clump. So if there's energy in space and I move an electron into that field of energy, it hits this bit, moves it, it hits this bit, moves it, hits this bit, moves it, hits this, and it ends up clumping all the energy essentially in one little block of space. So energy spread over this whole area ends up being condensed into this smaller area. And that's basically the function of electrons in this process, is to condense energy by moving quickly. The same principle could be argued as what affects magnetic induction. When you move a magnet quickly into an inductor, what you're doing is collecting a bunch of force, pushing it into the magnet all at once. And the atoms and electrons in the magnet can't react quickly enough to balance to that change in the electron pressure, and it creates voltage, for example. Alright, so the receiving end is likewise affected by polarization. So I would argue that when conventional physics will give you a couple of arguments about how photoelectric effect, which is the effect of popping an electron off of a surface, And then we have the other photoelectric effect, where all you do is cause an electrical current to move through a substance. Now the trick to making an electric current is I can hit a surface and the electricity could go lots of different ways. And it's only when there's a metal surface, that is some surface that's made of crystals, crystals connected to each other, that it's possible to create this idea of creating a potential on either side of the object. So the fact is that metals will take energy that's going this way, and the path will be between the crystals and it'll go that way. So no matter which way the electrical potential is, which way the little antennas are lined up, it converts it into direction eventually. So direction in this way electrically can end up being direction this way electrically. So the electrons will end up going one place and the lower potential will be at the other end. So that's something to be understood, as all this has to do with the kind of the chemistry of the materials, and whether they're capable of producing electricity is whether they're capable of detecting a photon, for example, using the substance to detect a photon's arrival. It is sort of dependent on it producing an effect that we can detect. So much of what we're saying when I say photon isn't really saying, okay, I'm just detecting the energy of the photon. I am detecting the pattern of the photon. So all the detectors are sort of dependent on the entire pattern being correct, and if the pattern isn't right, then you don't get the effect which we can measure, which we say is a photon. So if the frequency isn't consistent, if this is 200 nanometers and this is 500 nanometers, the material won't react in a way where it creates that electric current, or it creates an electron leaving the surface. So all of that has to be understood. Now I want to get to the filter part, because that's the interesting, well, it's all interesting. I have used this idea that the filter is this way and you're sending the envelope flat through this way. And it's a common mistake. I kind of knew it was a mistake. I know the argument is that the filter goes the opposite way of your intuition. So in a sense, the bars are this way and you're sending the envelope into the bars, in this way. Like, somehow that's not going to work. If I have the envelope this way and the bars are going that way, how does the envelope get through? But the thing to understand is the envelope has on it the polarization, so this is really what's going through the bars. And the idea would be is that these things are a wavelength separated, these bars. You can understand that, oh yeah, well, if the top piece goes through, this piece will go through, this piece will go through, and this piece will go through. So in some ways that's very consistent. And you could also understand, so the bits on the envelope can get right through there, because if this one's right, then this one will be right, this one will be right, this one will be right. If it's close to the bar, if this one's close to the bar, then this one's going to be close to the bar, and this one's going to be close to the bar, and this one's going to be close to the bar. And if they are close, the trick is what the bar is doing. I don't really know how to draw that other than just to say, you could say it's a substance. And the idea is that just as with slits in the two-slit experiment or the single slit, the idea is the light either reflects this way or it goes this way. So it goes around the surface. It doesn't go, it goes, if this is the impediment, it goes this way or it goes that way. It doesn't do this and it doesn't do that. So it's not going up and down, or in this case left and right. It's going around, or it's going deflecting off, because the electrons are on the surface. So you can understand the electron is either in this position, here's the proton. The electron's in that position, or it's in this position, or it's in this position. If you hit it, you can understand that it's going to tend to move this way, or it's going to tend to move that way. It's not going to go this way and that way. Alright. So that's a way to understand this, that even the light that does hit the bars, all the pieces of light will hit the bars in a similar manner, meaning that all of these bits could go down or they could go up, but they're not going to go left and right. So they're still going to be close to being a photon. They're now just going to have their polarization screwed up. So where their polarization going in was this. Now, because they went through these bars, they went by this matter, they went through a space that's different. These spacings aren't right. So now the polarization, this one, say, is being pushed, you know, its direction has changed a little. Now it's going somewhat in this direction. So now its position is off. And say this one did likewise, so its position is off. So now the polarization isn't quite correct. It could be much wider or it could be narrower, depending on which way the bits moved. And by changing their angle, you're also messed up the frequency a little. The distance between them now isn't as consistent. And so the trick would be, as you could understand, is you could set up a second set of bars, okay, in another pattern, where now there is going to be some deflections in other directions, you know, because now you're going perpendicular, tangential to the original direction, and now you're going to be moving photons into new positions where their old off angle is now going to put them back in phase, and so you can reconstruct the pattern. So going through two filters, you break it with this filter and then you fix it with this filter, and it's back to having its correct polarization. So that would be the idea of the function. Obviously the ones where you're going completely against, okay, the photons that go in and the filter's going this way, and the photon is going in the same direction, its polarization is this way, the envelope. Okay, so you know, the real bullets in space are sort of like this, you know, they're, you know, intervals between each other, but they're in alignment. But when they go through this filter, they're getting spread opposite their polarization. So where this filter spread them in the same direction as their polarization, this filter is going to spread them this way and that way. It's going to make them wider in these directions, which is going to be more, you could argue, destructive to being able to reform it back into something thin and, you know, that has the right shape. So again, it's just about a pattern. So it's a pattern going in, and all you're saying is can I make the pattern coming out? And it doesn't matter whether I make this bit of a photon, I have another photon here, it doesn't matter whether this bit becomes this one, and this bit becomes this one, and this bit becomes this one, and this bit becomes that one. It's just about pieces and rearranging the pieces. They just have an order, an A, B, C kind of order, and all you're trying to do is reconstruct the order. So a polarizing film doesn't absorb much of the light. Much of the light doesn't get killed by these bars. Even if they're made out of metal with a radio wave, very little of the total energy actually hits the bars. Most of it either rolls or bounces off the bars, or it just goes between the bars. So only a tiny percentage is affected by the surface of the bars, where there's a bunch of electrons and there's a bunch of capacity to have the little bits of energy scattered. And that's really the point, is that the energy is just scattered by the matter. So all you're really doing is putting something in the space, you know, an obstacle in the space that just has electrons on its surface. And you're putting that obstacle, okay, so this will kill the photon, right? If it hits this metal, the photon's going to reflect, it's going to get absorbed. It's not going to continue on its journey. But if it just hits an electron, it'll continue on its journey. It'll just be scattered in a new direction. And then if it goes between the bars, you can understand it's going to be unaffected, and it'll just continue in its straight line path, no problem. And so that's what you're really just talking about, is a percentage of the energy will be hit the bars, but it's only a tiny percentage of the total energy. The bars will affect some of the energy in terms of deflecting it, but the majority of the energy probably will go in between and not hit one of the bars. And that's consistent with all the kinds of filters. If I use metal bars to do radar, the percentage of bars to empty space is 10%, something less than that probably. So that's all perfectly consistent. Okay, so the final stage is hitting the surface, and what happens at the surface. So there's some theory that a single electron, moves in its orbital. So I can make an orbital here, and I move the electron to a different orbital, and somehow that's a photon. When, yes, the idea is the electron does move quickly. Okay, it jumps quickly between these energy levels, these orbits. And the orbits aren't orbits, I would argue. It's really, I don't want to spend a lot of time explaining what an atom is, but atoms are magnetic. It's really just about tension between the different parts. There's a huge attraction to the protons created by an absence of pressure, and there's a huge repulsion between the electrons. And you can sort of understand that if I'd made this out of magnets, and these were north end magnets and this was a south end magnet, that I could potentially create an arrangement where this magnet here, although attracted to the south end, can't get to it, because to get to it, it has to get closer. It has to move closer to these repulsive magnets, and so it's stuck. And that's sort of, I would argue, is the real mechanism of an atom. And what we're really talking about is can we hit this atom hard enough? I mean, this electron, or more specifically, say this electron, can we hit it hard enough to move it in here to the tighter orbit of the tighter orbital, the tighter distance, okay, where the magnets are also stationary, they're not orbiting, but can I push it into that, or can I push it out of that? And really we're just talking about, once I've done that, once I've given enough energy to do that, it does it quickly. And that quick movement is this quick movement. It's this movement that captures all the energy between me and you, and it reflects it all at once. So if I move quickly enough, I capture all the photonic energy in space. If I move quickly enough, and I push it at you all at one time. And that's sort of the principle. And if I go the opposite way, I do exactly the opposite. I don't reflect any energy to you. You see nothing coming from this object. I move it fast enough, it disappears. No reflections, no anything. And that's sort of the idea of what's creating the elements of a photon. The nodes are being created by those events. Okay, but the nodes, the sequence, needs more than one electron. You can't make a photon with just one electron moves and one electron moves back. You can't make a photon out of that. You need that to happen here, and you need it to happen again over here. So that will create the photon. That's what's going to create the pattern. And it's not going to create one photon, in the sense that it's not going to create just one piece of energy that's going to bounce off that electron. It's going to be a group of energy. So it'll be a group here, and a group here, and a group here. And all of these will be connected to each other as a potential photon. That's a potential photon. This is a potential photon. This is a potential photon. So it's going to create more than one photon going through space. See, these happen at different events, so I should draw that a little differently. Just like the antenna argument, you're creating a grouping here. That grouping moves away. You create another group here. That group moves. You create another group here. That group moves. And you can understand that this one keeps going as these are being created. And so this group is here. This group of bits. There's a group of bits here. And then there's a group of bits here. And if you add those up as individual objects, that's like 6 photons, or 10 photons, or 100 photons. If you take the individual bit here, one individual bit, one individual bit, one individual bit, that's a photon. Well, this individual bit, this individual bit, this is potentially a photon. And that's what's hitting a surface, is a collection of those events. And so on the receiving end, it's pretty much the same idea with the antenna argument, is that in metal crystals, for example. The idea is you hit the surface, and what are the little bits are coming, and they're going to hit this surface of atoms. And where they're going to, the idea is this one has to hit an atom, I mean an electron, okay, and it has to, before the electron can go back, you know, so you're trying to push an electron, so an electron is here, and you're trying to get it here. Well, the only way you can do that is you hit it, and you have to hit it again before it springs back, or it's not going to get here. So to get it to go to the new position, you have to hit it twice. So another bit has to hit it, and that has to push it in. So it takes more than one event. That's why there's a rule to popping electrons out, where it has to be blue light or better. You know, it has to be ultraviolet or better to ionize the atom, to knock the electron free, because you have to hit it within a certain time. And if you wait too long to hit it, like infrared is twice as long, if you wait too long to hit it, it's already gone back. You're too late. You can't get this distance because you didn't hit it. You can't get enough speed. And the way you can get the speed is you have to hit it, get it moving, and hit it again before it stops and starts heading back. So the idea is to hit it again before that happens. That'll free the electron. Now, to make electricity is a little subtly different. You don't need as much energy. You can do it with infrareds. I mean, you can do it with a red and above to make it a visible photon, but you can certainly detect infrared, lots of different other kinds of frequencies, because all you really need to do is create electricity. So all you really need to do is, the atoms are sitting here. You don't need to force the ionization. You don't need to kick the electron out. All you need to do is cause the electron to be under a higher pressure, that is, switch its orbit. So go from an inside orbit to an outside orbit. That screws up the next atom, okay, which wishes to convey that pressure to somebody else. You're putting this atom, by having an electron go to the outer orbit, it's basically saying to the next atom, I'm more negative now. I'm putting more pressure on you. So the next atom tries to exchange that pressure, and the next atom tries to exchange that pressure. And the idea is just you cause the effect here. You have to magnify the effect by hitting within a certain frequency, a certain distance of time. Within that distance of time, you have to hit it again to cause it to maintain the flow of the electricity. So that's the dependency of the photon on hitting it more than once. Okay, maybe it's 3 times, maybe it's 4. Who knows what the minimum is to cause the electrical current that's going to say, okay, that's a photon. We got enough energy to call it a photon. And that's what your brain has to do. Your eye can only collect the pattern. It has to get hit in the right sequence to push the electron continuously, and it has to push it with enough pressure to cause a sustainable pressure. That is, a pressure that will keep moving. So it has to get up to a fast enough speed where, like in the case of sound, for example, to make a sound you got to move faster than the sound barrier. Well, these atoms, depending on their chemistry, depending how thick and big and all that stuff they are, have their own sound. They have their own speed of sound. They have their speed of electrical conduction. And you have to go a little faster than that. You have to get the electron to move faster than that to get it to propagate in a straight line. Otherwise, the energy will go in other directions. It'll go this way, it'll go that way, it'll go this way, because the electrons will have time to balance. The other atoms will have time to balance if you go slow enough. Just like in an inductor, if I did have an inductor and I'm going to push a magnet into it, I have to push quickly. Not only because I have to push force, I have to collect force and push it, but I have to cause the effect where these atoms on the surface don't have time to spread the pressure. So extra pressure is coming into them, pushing on them, and I have to cause it so the pressure is so great that it can only go in one direction. It can only cause this positive negative effect in the wire where it's going to force it to flow in one direction. So when it's sort of just like that for sound, you have to have movement that's quick enough that it breaks the ability of the energy to be spread. And the energy can only be conveyed in the direction of the momentum. That's the idea. And obviously the direction of the momentum means based on like the compressibility of the substance. So obviously water, not obviously, but I can make the argument that water is doing the same thing. When you make waves on the surface, you're really pushing energy this way, and the fact is it's not compressible. And the only real option, because this is matter here and there's matter behind it, and there's a floor to the sea here that's hard, the easiest direction to go with the pressure is this way, because it's just weak atmosphere. The downside is there's gravity up there, so what happens is as you push up, the gravity pushes back down again and now causes energy to move in this direction, and now that energy has nowhere to go. Okay, there's greater pressure this way because that's where the initial pressure is coming from. There's still, the ground is too hard, you can't go that way, so it's stuck going this way, and it just repeats the same pattern of pushing up, and then the gravity pushes back down. So the atoms in the structure of a material are bound by the same kind of laws, the same rules, not laws, and they're going to end up efficiently moving. The faster you move something, the more efficient is sort of the argument. So if I shoot a bullet at you really slowly, 10 miles an hour, the bullet's going to make a lot more mess, right? Because it's going to hit the surface of your skin, and it's going to cause deformations in all kinds of directions, and it's going to tear and rip and shred and do all of that kind of stuff, because there's plenty of time for all the atoms to get involved, to spread the energy across a whole bunch of atoms. But if I move the bullet very fast, these atoms don't have any time to react. They don't know anything happened. They have no clue. And the only atoms that are going to react, and they're going to act very violently because they're going to get hit very violently, all the energy is going to go through them. And they're going to, that momentum is going to go faster and faster, and it's just going to keep doing the same thing. It's just going to plow through a very small number of atoms rather than affecting a whole bunch of atoms. So you're not spreading the energy in all directions. You're only spreading the energy in one direction. That's the key to creating electricity. So anyway, all these subjects are related and connected, but I guess the key argument is to say, yes, I acknowledge that a polarizing filter is actually aligned anti to how you would think it would work, because the envelope isn't a rigid thing. The envelope is just a way of understanding the idea of the polarization being a bar coming at you. Okay, the idea isn't that it's a solid thing. The bar is made of pieces, and the pieces can get through the bars going horizontally. The polarization is this way, but the pieces find that totally comfortable. That's easy to get through. And again, it's intuitive to the sense that the good news is now if you're going to have any deflections, the deflections are up and down, and so you're not going to spread the photon into some horrible mess that you can't reconstruct by spreading them perpendicularly. The one going through this way, okay, could go straight through the bars that way, but the problem is that any being off a little bit means that you're going to send a bit that way. So it won't be in line with the polarization anymore. You're sending it off the polarization, which means it's very unlikely you're going to be able to reconstruct that photon. It's going to be catastrophically broken. Alright, I think that's enough, and such, and so forth and whatnot. I think I covered the key points, mostly. So, as of November 23rd, that's most of the story of polarization.